For his ninth problem, Hilbert was after the most general reciprocity laws for any algebraic field. Let's start by saying what an algebraic field is. An algebraic field is just any set of numbers for which addition, subtraction, multiplication and division all work. So the rationals is the most basic algebraic field because not only can you multiply any two rationals together and get a rational number out, but you can do the same with division. But the integers are not an algebraic field because although multiplication works and you always get an integer out, if you try to divide 3 by 2, for example, what you get is not an integer. And so you might say, well, what kind of equations can we generally solve on an algebraic field? For example, for the rationals, does the equation x squared equals 4 have a solution? Well, yes, it does. It's either 2 or minus 2. But what about x squared equals 3? Well, no, because neither root 3 or negative root 3 is a rational. But then you might ask, well, what about congruence relations? Instead of equality, what if I asked whether there is some number x squared which is equal to 3 mod 11, let's say, or rather is congruent to 3 mod 11, to be more precise. And that's just to say, well, is there some number where x squared divided by 11 has the same remainder as 3 divided by 11, or equivalently, where x squared minus 3 is some multiple of 11. And it turns out, just for this toy example, that yes, there is. It's 5. 5 squared is 25. You can take 11 away from that twice, and you end up with 3. But here is the amazing thing. Equations like this, where you have two primes, p and q, in our case 3 and 11, but equations where you have any two primes, it turns out that there is an intimate and surprising relationship between whether one prime is a perfect square mod the other and the inverse. So whether p is a perfect square mod q depends on whether q is a perfect square mod p. And this is super surprising. And actually, Gauss, who discovered this, called it his golden theorem. But more generally, this is called the law of quadratic reciprocity. Quadratic because it involves squares, and reciprocity because of this funny, intimate relationship between the two primes going in. And what Hilbert wanted was a general law like this, not just for quadratics, but for all orders of equations and for all algebraic fields. And that's a lot, because there's an uncountable number of algebraic fields.